getting into my own talk, it's going to be about an overview of the Siesta code. And as you probably, most of you will know, Siesta itself is a density functional theory code. It is like many others in many ways, but from its very inception, Siesta was aiming for efficiency. So it was a code that was devised in order to be able to do density functional theory calculations much more efficiently. And efficiently means you can do larger simulation boxes, pack in more atoms of different kinds, and that opens applicability to lots of different kinds of contexts and complexities. So that's a reason for the efficiency at the time. And actually it was the very first fully self-consistent linear scaling density functional theory code in the 90s. And linear scaling meaning that the computational effort, both in CPU and memory, would scale with the number of atoms instead of the cube of the number of atoms. That is the conventional scaling for density functional theory complexity in the codes. So the Siesta code is based on atomic orbitals that are used as basis sets. And it is something which is very conventional, for instance, in traditional quantum chemistry. It's nothing new. And these atomic orbitals are constituted by functions that are the product of a radial shape and an angular shape for this functional. The angular shape is just spherical harmonics of the kinds that you're probably familiar with, S, P, Px, Py, Pz, and so on and so forth. And the radial shapes, we'll come back to them in a moment. So the disadvantage of this kind of scheme is that convergence with basis set is much more laborious. It's not systematic or automatic as you could do it with things like plane waves. And it is responsibility of the user to choose the right basis set for your problem, your system, the kind of accuracy you need, and so on and so forth. And so it's, again, more laborious and less automatic. But it has as an advantage, the key advantage is that you need much fewer basis functions per electron are needed, and that impinges a lot into the efficiency of the calculations. Rule of thumb, as I have here, is that you may need of the order of 3-5 functions per electron for the calculations for which you would need of the order of 100 plane waves per electron. So since these numbers affect very much the sizes of the matrices you have to, for instance, diagonalize, then that's going to impinge very clearly into the efficiency of the code. Again, not new, and many other codes are using similar technologies of atomic orbitals as basis sets. Of course, most of the quantum chemical ones, and you have here some of them, QChem, NWChem, ADF, Gaussian turbomole, but also some that come more from the physics community like DMOL, F8A, AIMS, CP2K, that are codes you may know in addition to Siesta. Now, going a little bit more to the peculiarities of Siesta itself, and actually of the Siesta method, we are going to be using finite support for the basis functions. And that is the radial shapes that I was talking about for the atomic-like orbitals. They're going to be such that they are actually confined strictly within a radius from the center of that orbital. And from then on, they are strictly zero, as compared with traditional basis sets in which there was a decay, but the decay would not really go strictly to zero up to infinity. That means that the matrices we're dealing with are going to be strictly sparse. We won't need to neglect or cut matrix elements a posteriori. Actually, the zeros in the matrices are going to be exactly zeros. And as long as, this is a key point in Siesta, as long as you have finite support basis functions with a radial times spherical harmonic shape, the rest is up to you, the user. You can put as many as you want, whatever you want, and of any radial shape you want. In this instance, I normally say that if you want to put the New York skyline as your radial shape, is your problem. You can do it if you wanted to, and if it's good for your calculations. So using that, let me state, for instance, let me put it in as the two key components from the computation point of view of a typical density functional theory code. You have one bit in which, given a density, particle density, electron density in your problem, you compute the Hamiltonian for your particular problem, the Kohn-Sham Hamiltonian. So the computation of the matrices and matrix elements, when you have the finite support I was talking about, together with a discretization of space, here you have a cartoon, your finite support basis functions in 2D, and discretization of space. Actually, once you convert this into lists and sparse matrices, you can get to algorithms that would be absolutely always linear scaling and computational effort. So the calculation of the Hamiltonian and overlap matrices are always linear scaling within Siesta. And that was at from the very beginning of the Siesta method. And that is a key for the efficiency of the Siesta code. Then there is a second step, which is given the Hamiltonian matrix and the overlap, you want to get the energy and the density itself, that is solving the Kohn-Sham eigenproblem. Originally, Siesta was devised with linear scaling solvers that were based on localization of solutions. So here, again, here on a cartoon basis, if you have these smaller circles, filled circles as the pseudopotentials, if you want, the ions, and then the bigger one, the slightly bigger ones are the finite support region for the basis orbitals. You have a much bigger ones, the solution wave functions that we're after. You can think of them as Wannier-like solutions of your problem. Of course, that would be for insulating or semiconducting problems. That was everything we had at the very beginning of Siesta. Since then, it has evolved, and now we have many different solver options or various solver options, from linear scaling to cube scaling, involving conventional diagonalization of different flavors, and so on and so forth. But there will be a talk dedicated to that, so let me not expand much more.